Welcome to our journey into the quantum realm. Today, we begin by understanding a fundamental concept in quantum physics, the Planck length. The Planck length, approximately 1.6 x 10 circumflex 35 meters, is considered the smallest measurable length in the universe. To put this into perspective, it's about 10 circumflex 20 times smaller than the diameter of a proton. Imagine shrinking down to such an infinitesimal size that the very fabric of space-time itself becomes grainy and discontinuous. Named after the German physicist Max Planck, this length scale is derived from fundamental constants, the speed of light, the gravitational constant, and the reduced Planck constant. These constants combine to define a scale where classical concepts of gravity and space-time cease to apply, and quantum effects dominate. Understanding the Planck length is crucial because it sets the stage for exploring the limits of our physical theories. It challenges our understanding of the universe and beckons us to venture beyond the known, into the mysterious realms where the laws of physics as we know them may no longer hold true. Let's dive deeper into this enigma and see what lies beyond the minuscule Planck length. Welcome back, adventurers of the quantum realm. Now that we understand the Planck length, you might be wondering, can we go smaller? The short answer is, theoretically, yes. But how do we even begin to explore these sub-Planck lengths? One approach is through the concept of quantum foam or space-time foam, proposed by physicist John Wheeler. Imagine the fabric of space-time at the Planck scale, not as smooth and continuous, but as a frothy, turbulent sea of ever-changing geometries. In this chaotic landscape, distances smaller than the Planck length could fluctuate wildly, making it a challenge to define or measure them with any certainty. Additionally, some theories suggest that at these minuscule scales, space-time might have a fundamentally different structure. For example, loop quantum gravity posits that space-time is composed of tiny loops, each with a discrete area and volume. These loops could be far smaller than the Planck length, hinting at a hidden layer of reality. String theory, another contender in the quest for understanding, suggests that the smallest building blocks of the universe are not point-like particles, but one-dimensional strings. These strings vibrate at different frequencies, giving rise to the particles and forces we observe. The scale at which these strings operate could be much smaller than the Planck length, opening up a whole new world of possibilities. Exploring these ideas requires advanced mathematics and high-energy experiments, pushing the limits of our current technology. Particle accelerators like the Large Hadron Collider are already probing the boundaries of our understanding, but future advancements in technology and theory will be essential for uncovering the secrets of the Sub-Planck realm. As we continue our journey, remember that the quest to go smaller is not just about measuring distances, it's about expanding our understanding of the universe. Each step forward brings us closer to answering some of the most profound questions in science. So stay curious and keep exploring. Up next, we'll delve into the mind-bending theories that lie beyond the Planck length. Stay tuned. Welcome back, explorers of the infinitesimal. Now that we've traversed the chaotic landscape of quantum foam and the mysterious loops of quantum gravity, let's dive into some of the mind-bending theories that suggest what might lie beyond the Planck length. First up, we have the concept of extra dimensions. String theory postulates that our universe might have more than the familiar three spatial dimensions. These extra dimensions could be compactified or curled up at scales much smaller than the Planck length. Imagine dimensions so tiny that they are imperceptible to our current instruments, yet they could hold the key to unifying all fundamental forces in the universe. Another fascinating idea comes from the realm of non-commutative geometry. This mathematical framework suggests that at incredibly small scales, the very coordinates of space-time might not commute, meaning the order in which you measure them affects the outcome. This could lead to a fundamentally new way of understanding space and time, where the concept of distance itself breaks down. Then there's the speculative but intriguing notion of preons. Proposed as subcomponents of quarks and leptons, preons could be the true fundamental building blocks of matter. If preons exist, they would be far smaller than the Planck length, offering a glimpse into an even deeper layer of reality. Lastly, we have the idea of quantum gravity crystals. Some theories suggest that space-time could be akin to a crystal lattice at the smallest scales. These crystals could have a periodic structure, much like the atoms in a solid, potentially revealing new properties of space-time that are currently hidden from us. Each of these theories pushes the boundaries of our understanding, challenging us to think beyond the limits of what we can currently measure or observe. The quest to uncover what lies beyond the Planck length is not just about exploring smaller scales. It's about reimagining the very fabric of reality. As we continue our journey, remember that every new theory brings us closer to unlocking the deepest mysteries of the universe. Stay curious, stay imaginative, and keep pushing the boundaries of what we know. Up next, we'll venture into the realm of sub-Planck lengths and explore what might lie beyond the minuscule. Don't go anywhere! Welcome back, intrepid explorers of the quantum unknown. We've journeyed through the theories and possibilities of what lies beyond the Planck length, but now it's time to address the ultimate question. Will there ever be something smaller than the Planck length? To answer this, we must first understand the limitations of our current scientific tools and theories. The Planck length, at approximately 1.6 x 10 circumflex 35 meters, is derived from fundamental constants in physics. It represents a scale where our conventional understanding of space and time breaks down and quantum gravitational effects become significant. But science is ever evolving. The development of new technologies and mathematical frameworks could potentially unveil measurements and phenomena beyond the Planck scale. For instance, advancements in particle accelerators or the discovery of new particles could provide insights that current instruments cannot. Moreover, theoretical physics is constantly pushing boundaries. Concepts like quantum foam suggest a seething, chaotic underpinning to spacetime at scales smaller than the Planck length. Additionally, loop quantum gravity and other emergent theories propose that spacetime itself might be quantized, implying even smaller units of measurement. The idea of a theory of everything, a single all-encompassing framework that unifies general relativity and quantum mechanics, could bring us closer to understanding these sub-Planck scales. Such a theory might reveal new dimensions, particles, or forces that operate beyond our current limits. However, it's important to note that the Planck length is not just a physical limit, but also a philosophical one. It challenges our very notions of measurement and reality. As we delve deeper, we may find that the question isn't whether something smaller exists, but how we define and perceive smallness itself. In the end, the quest to discover what lies beyond the Planck length is as much about expanding our minds as it is about expanding our scientific horizons. It's a journey that compels us to rethink the very fabric of reality and our place within it. So, will there ever be something smaller than the Planck length? The answer lies in the future of scientific discovery, driven by curiosity, innovation, and the relentless pursuit of knowledge. Stay tuned, because the universe always has more secrets to reveal.